So the topic of this video is a review of a subject that you studied in Calculus 2. And it's a subject that we're going to need now because it gives us an alternate way of solving some differential equations. That subject is power series. So recall, the power series centered at the x value x equals x naught is a formal expression of the following form. A naught plus a1 x minus x naught plus a2 x minus x naught squared plus a3 x minus x naught cubed plus and so on forever. And I can write this using sigma notation. I can write this as the sum as n goes from 0 to infinity of a sub n times x minus x naught to the nth power. This is just a nicer way, shorthand way of writing this. If I write my power series around x equals 0, then this looks a little bit simpler. We write this as a naught plus a1 x minus 0, in other words, x plus a2 x squared plus a3 x cubed plus and so on forever. And I can write this using sigma notation if I like. N goes from 0 to infinity, a n x to the n. So when you look at it like this, if we have a power series around x equals 0, it looks a lot more like a polynomial, but polynomials have finite degree. The largest power of x is 5, and the degree of the polynomial is 5. If the largest power of x is 1,000, the degree of the polynomial is 1,000. A power series goes on forever. And as a notational thing, usually when we write polynomials, we write the largest power of x first. Since there is no largest power of x when we're writing power series, we tend to write the constant first, and then the linear term, the quadratic, the cubic, and so on. So these a's are just numbers. So for instance, if let's say all the a's are 1s, then I have 1 plus x squared plus x cubed plus and so on. All my coefficients are 1 this time. I just put a 1 in front of every power of x. This is a power series around, you can see that this looks just like this, so it's a power series around x naught equals 0. Just as an example, you can put any number in front of any power of x and it's still a power series. They don't all have to be the same. You could have 1, 2, 5, 8, whatever. They can all be different. So hopefully power series as a subject is coming back to you. If not, take a look in your calculus textbook. You will see a whole chapter on sequences and series. Close to the end of the chapter, you will start to see things about power series. Now I want to remind you about Taylor series and Maclaurin series. Say we have a function f of x. And this function is infinitely differentiable, and I'll explain what that means in just a second. So infinitely differentiable. That means that at x equals x naught, not only is the curve smooth, so you can take its derivative once, but once you have the derivative, that's smooth, and so you can take the derivative again. And once you have the second derivative, that's smooth, so you can take the derivative again. That you can take the derivative infinitely many times at x equals x naught. So this curve is infinitely smooth. There are many curves that are infinitely smooth. In fact, most of the ones you're used to dealing with. Every polynomial is infinitely smooth. Every rational function is infinitely smooth wherever it's defined. Sine and cosine are infinitely smooth everywhere. So is e to the x. So is any exponential function. So is the logarithmic function wherever it's defined. All these functions are infinitely smooth. So this isn't actually all that big a restriction in terms of the functions that you're used to working with. If you have absolute value of x is not even once differentiable at x equals 0. Of course, it has a sharp turn at x equals 0, shaped like a v, has a sharp turn there. And you can come up with functions that are smooth, so they're once differentiable, but when you take the derivative of the derivative, they fail to be differentiable. So if you can't think of an example of that, feel free to ask me and I'll help you through an example. So say we have a function which is infinitely smooth at x equals x naught. And say we define a function, say we define a power series like so. We will just take f of x naught. This will be our constant term. Since I'm just taking f and plugging in a number, I get a number. Plus f prime of x naught over 1 factorial times x minus x naught plus f double prime of x naught over 2 factorial x minus x naught squared plus f triple prime of x naught over 3 factorial x minus x naught cubed plus and so on forever. And again, I can write this in sigma notation. So the sum as n goes from 0 to infinity of the nth derivative of x naught, where it's understood that the 0th derivative is just the original function itself, divided by n factorial. And again, I'll remind you that 0 factorial is equal to 1, x minus x naught to the nth power. This is just a shorthand notation for what I've written here. Then this is called the Taylor series. For the function f centered at x equals x naught. Let's take a look at an example. Write the Taylor series for f of x equals e to the x centered at x equals 0. So hopefully this is in your notes by now. I can go ahead and erase it. Maybe I'll just try to leave that there and do my work over here. So to be able to do this, we are going to need the derivatives because we need to plug the derivatives in. So in this case, it's quite easy. F of x equals e to the x. F prime of x, the derivative of e to the x is e to the x. F double prime of x is e to the x. F triple prime of x is e to the x, and so on forever. I'm plugging in x naught. X naught in this case is 0. So f of 0 is equal to e to the 0, which is 1. F prime of 0 is equal to e to the 0. That's 1. F double prime of 0 is equal to e to the 0. That's 1. F triple prime of 0 is equal to e to the 0. That's 1, and that continues forever too. All of these derivatives at x equals 0 are 1. So now it's just a matter of plugging everything in. F of x 0 is 1. F prime of x 0 over 1 factorial, that's just 1 over 1 factorial, 1 over 1 times x minus 0 times x. F double prime, which is 1 over 2 factorial, 1 over 2 factorial, x squared, 1 over 3 factorial, x cubed, 1 over 4 factorial, x to the 4th, plus, and so on. Now I'm going to ask you to remember something from Calculus 2. You might recognize this as the Taylor series. The Taylor series centered at 0, which we also call a Maclaurin series, for e to the x. If you want to remind yourself of what that has to do, let's say you wanted to compute e, the number e. Then all you do is plug, since e is e to the 1, all you do is plug a 1 in everywhere you go over here. Now, as you go more and more terms, these terms are getting smaller and smaller because that's just going to be 1 cubed over 3 factorial, 1 cubed over 4 factorial. The next one will be 1 cubed over 5 factorial, and so on and so on and so on. So if you want to figure out what e to the 1 is to, say, 3 places after the decimal, just plug in enough terms, putting a 1 in for x, so that when you get that far, the terms are getting so small that they don't change the first 3 places after the decimal. And you'll find that e equals 2.718, and you can find e to any level of accuracy that you want. Let me talk about one more thing. At least one more thing. A power series whether or not it's a Taylor series, in other words, whether or not it comes from an f of x or not, or you just create it out of nowhere, a power series centered at x equals x naught converges, and again, I'm going to, if the idea of convergence of a series is something that's a little bit rusty, go review your Calculus 2 text. Converges either, there are 3 possible things that can happen. It might converge just at x equals x naught. Might converge just at x equals x naught. Secondly, it converges on an interval of positive radius centered at x equals x naught. Radius for an interval is the same thing as the radius for a circle. It's the distance from the middle to the outside. For example, if x naught is 1, so here we are 1 on the number line, then let's see, here's 0, here's 1, here's -1, here, oops, this would be 2, here's 3. Then the interval, let's say -1 to 3, is an interval that's centered at 1. 1 is right in the middle of that interval. 1 is 2 units away from -1 and 2 units away from 3. The radius of that interval would be 2. The distance from the middle of the interval to the outside. So this interval, if I was going to sketch it on this picture, open circle at -1, closed circle at 3, all the stuff in between. And in your Calculus 2 course, you would have discussed examples where we converge on a finite interval with positive radius, and sometimes it's a closed interval, you include both endpoints. Sometimes open interval, you don't include either endpoint. Sometimes like this, it's a half open interval, you include one endpoint but not the other. All of these are possibilities. And there's a third possibility, so either it converges just at x0, which is like a very short interval, x0 to x0, or it converges on an interval centered at x equals x0, or it converges everywhere. Say from -infinity to infinity. So any of these three things are possibilities. If power series and Taylor series are only sort of vague ideas in your mind right now, I urge you to pull out your calculus textbook, look at the relevant sections, and ask me any questions you might have about them.